Welcome. Today we're going to be looking at probability. But before we do that, we really need to learn how to count. We're going to learn in this lesson how to count the number of permutations for some sort of event, for some sort of task. We're going to learn how to count permutations when order matters, and we're going to learn how to count permutations when we have repeated objects. So let's just talk about probability first. We have this notation. The probability of some event is written as P with parentheses and the description of the event inside the parentheses. Now, the probability of an event happening is this ratio, the number of outcomes of an event divided by the total number of outcomes. And here's an example. The probability of rolling a 1 or a 2 in a 6-sided die would be, well, there are two possible ways of rolling a 1 or a 2, and then there are 6 possible ways of rolling a die, 1, 2, 3, 4, 5, or 6. So 1/3 of the time we're going to be rolling a 1 or a 2. So this is a simple case where we can very easily count both the number of outcomes in the event and the total number of outcomes that are possible. But sometimes it's not easy to count, and so today we're really going to concentrate on how do we count. Once we learn how to count better, then we can then use that in kind of calculating more challenging probability kind of events. So we're going to start with the fundamental counting principle. Let's look at this. We have, say, 3 types of cars, and 4 different colors that we can choose. The question is, how many possible different cars can be chosen with these different colors? So we can think about it as a tree. We can choose a Civic, we can choose Neon, we can choose a Prius. And for each one of these car choices, we can choose any one of the 4 colors. And we can replicate that then for each of the 3 different cars. So altogether, you can see that we have actually, if we count all of these up, we have 12 different choices of how we can select a car. And we could think of it actually as 3 choices here. We had 3 choices for the type of car, and then 4 choices then for the color. So 3 times 4 was equal to 12. So this leads to the fundamental counting principle, so that, say we have 3 events. We could have more than 3 events, but just in this case, say we have 3 events. Event 1 can happen in M ways, event 2 can happen in N ways, event 3 can happen in P ways. The total number of ways, this is counting here, how many different ways can all these events occur is M times N times P. Okay, so here's a little bit more complicated example where we have 8 different shoes, 5 different colors of socks, 7 different pants, and 10 different shirts. How many different outfits are possible if I just, select different kinds of shoes and whatnot? So I could start with 8 different shoes. I multiply that times 5, multiply that times 7, multiply that times 10, and I get 2,800 different kinds of outfits that are possible. Let's look at another example. California license plate. In the old days, there used to be only 3 numbers and 3 letters. How many cars could be licensed under this scheme, 3 numbers and 3 letters? The way I like to build this out is I like to kind of think of it, I kind of build this up where I put these kind of blanks here for the numbers and for the letters. For the first number, there are 10 different possibilities, from 0 to 9. For the second number, I have again 10 different possibilities to choose, so I multiply times 10. The next number, again, 10 more choices, 0 to 9. Now for letters, I have up to 26, so 26 times 26 times 26, and that equals 17 million different kinds of license plates available. So I could have 17 million unique cars before I have to start duplicating license plates numbers. Now suppose I had a restriction and I don't want any replicated letters anywheres in my license plate. No repeated numbers, no repeated letters. So I'm going to start again with this template. Now the first choice I do have at my disposal 10 different numbers to choose from. But after I've chosen one, say I chose a 5, then I'm only left with 9 choices left for this next number. And after I've chosen that number, say I've chosen a 5, then I chose a 2, I only have 8 numbers left to choose from there. Now then when you go to the letters, I could have 26 letters to choose from for my first letter, but then subsequently I only have 25 letters, and then finally I only have 24 letters. So in this case, the total number is a little more than 11 million. Which makes sense because since I restrict myself, I can't have quite as many choices as if when I did not restrict and I did allow repetition. Okay, there's this concept of permutations. Permutations is defined as an ordering of n different objects. So, for example, if I have 3 different objects labeled A, B, and C, I can permute them. I can write out different orders. These are each what we call different permutations of the letters A, B, and C. There's no more additional ways I can write out all these letters. One way to think of that, well, there's 6 of them here, but I could think of it as the following. The first one, I had 3 choices, A, B, or C. But once I chose that, now I only have 2 choices for the next letter. And then I only have 1 choice for the last letter. That's equal to 6. And we could see that what we wrote out, we had 6 combinations, or permutations I should say, and we calculated 6 as well. Now we have a shortcut way of writing this. 3 times 2 times 1 is okay to write when it's a small number like 3, but say we had 10 letters or 20 letters. Writing out 20 times 19 times 18 times 17 times 16, that requires a lot of just work. So mathematicians, we created this symbol, n factorial. It means n times n minus 1 times n minus 2 all the way down to 1. So if I have 7 factorial, it's 7 times 6 times 5 all the way down to 1. So another way of writing this up here, instead of 3 times 2 times 1, we can write that as 3 factorial. So this leads to the idea that there are n factorial permutations, ways to rearrange n different objects. So here's an example of that. Say there are 6 people running in a race. How many different ways can they finish the race? Well, there are 6 different people that could finish first, then 5 that can possibly finish second, and so on and so forth, all the way down. We can write this in an abbreviated way, 6 factorial. How about the top 3 finishers? Well, there's 6 different people who could win the race. There are 5 different runners that can get second, and 4 different runners then can get third place. We write that as 6 times 5 times 4. Now we're going to learn about a shortcut way of writing this as well. And we call this a permutation of R objects taken from a total of N objects. So we have this special notation, N capital P R. We can say N permute R as a way of saying, given a total number of N objects, if I only want to pick a smaller amount, R objects from that, how many different permutations are there? So here's an example, 6p3, 6 permute 3, so 6 factorial divided by 6 minus 3 factorial, which is equal to 6 factorial over 3 factorial, which we can expand out now. 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1, and these will cancel out, so we're left with 6 times 5 times 4, which is another way of writing out this previous case over on the last page right down here. So 6 times 5 times 4 can be written out as 6 permute 3. 6 total runners, and we're picking out the 3 top runners. Okay, so let's see how we can use this in another example. Say I have 100 songs in my iPod, and I want to make a playlist of 4 songs. And I do care about the order, so order is important. So in this case, I could say that my answer is 100 permute 4. Out of 100 songs, I want to pick 4 in a very precise order. So in this case, we have 100 factorial over 96 factorial. And this is equal to 100 times 99 times 98 times 97. So here's a couple practice problems you can try out on your own. This will use a variety of techniques that we talked about earlier. Now suppose we have repetition. Let's see how this is subtly different. I start with having 3 balls, but in this case one of them's blue, but 2 of them are the same. They're both purple. Now if I treated them differently, all the balls differently, I have 6 combinations, 3 factorial ways of permuting those 3 different balls. But in fact, so 3 factorial ways of permuting different ones, but in fact the purple ones are exactly the same. And so we can't really distinguish this from this or this. So these are kind of indistinguishable kind of combinations of them. So what we do is we divide it down by 2 factorial. 2 factorial comes in because we have 2 purple balls that can be rearranged in 2 factorial ways. So we take 3 factorial divided by 2 factorial, which is equal to 3. So I have 1, 2, and 3 unique kind of combinations of purple and blue balls. Okay? Let's look at another example here with 10 balls. We're going to start with the number of total permutations of 10 balls, pretending that they were all different. In this case, we have 10 factorial ways of permuting all 10 of those balls. But now we need to divide out the repeating cases. So let's start off with the red. There are 3 of those, so there are 3 factorial ways of permuting 3 red balls, 4 factorial ways of permuting 4 different blue balls, and then 2 factorial ways of permuting 2 purple balls. So once we divide this out, then we have the number of distinguishable permutations where we're not counting kind of this case twice. So this is some practice problems for you to try out. That's the end of this lesson.